This is Chapter 9, Principles of Joints and Sealants, Part 2. Okay, let's take a look at expansion and contraction control with moisture movement. Materials such as steel, copper, aluminum are dimensionally stable with respect to moisture. However, wet materials such as Portland cement shrink due to moisture loss. Because the moisture loss continues for several weeks after construction, Portland cement-based components keep shrinking long after they are placed in a wall or a slab. Therefore, concrete slabs, concrete and concrete masonry walls, and stucco require shrinkage joints, more commonly referred to as control joints. Clay masonry units are considered a dry material. Clay masonry expands on absorption of water or water vapor. This expansion occurs during and after construction, is irreversible. That is, clay masonry does not shrink on drying. In fact, a brick unit is smallest in size when it comes out of the kiln, after which it grows in size. Thus, brick masonry walls require expansion joints. So moisture movement is the coefficient of moisture for a selected material multiplied by its length. Let's take a look at this example. Expansion joints are to be provided in a brick veneer wall at 25 foot on center. Determine the moisture expansion of each 25-foot wall segment. So if we take a look at table 9.2 in your text, the moisture coefficient U of clay masonry is 3/10,000, 0.0003. Therefore, from equation 2, the moisture expansion of each 25-foot segment is 0.0003 times 25 times 12, which is 0.09 inches. So our clay masonry wall is going to expand approximately 1/8 of an inch in 25 feet. Let's take a look at a slab on grade. If control joints are provided in a reinforced concrete slab on grade at 12-foot intervals, determine the required width of each joint. So from table 9.2, U is equal to 0.0003. From equation 2, the minimum width of each joint is 0.0003 times 12 times 12. So we're converting the 12 feet to inches, and in doing that, we have to multiply 12 times 12. So our total joint width is going to have to be a minimum of 0.043 inches. So that joint's going to end up being about 1/2 of an inch thick. Let's take a look at wood. As discussed in greater detail in Chapter 13, the microstructure of wood consists of hollow cellular tubes bundled together. The walls of the tubes shrink and swell depending upon the ambient air's humidity and temperature, changing the dimensions of the wood member. So wood it's a different animal than concrete or masonry types of products. So the wood industry has established empirical rules for providing movement joints in wood members. For instance, a 4x8 sheet of plywood must be provided with 1/8 of an inch wide joints at ends and edges in order to accommodate its movement. Moisture-related movement control in wood structures is discussed further in section 15.11 in your. Let's take a look at elastic deformation and creep. Consider the beam in figure 9.15, which is initially unloaded, as shown by the dashed lines. If the beam is now loaded, it will deflect almost instantaneously in response to the load. Let the instantaneous deflected shape of the beam be represented by profile A. If this load is a permanent load, the beam's deflection may progressively increase and eventually assume the deflected profile B. This time-dependent additional deflection of the beam is known as creep deflection, and the associated phenomena is called creep. Thus, creep is the incremental deformation of a component caused by sustained loading. Among the structural materials used in buildings, creep is significant only in concrete and concrete masonry. Steel does not creep. In wood, creep deformation is relatively small. If a non-load-bearing wall is placed directly under a spandrel beam, adequate space between the beam and at the top of the wall should be provided to allow the beam to deflect under load. If adequate space is not provided, the load from the beam will be transferred to the wall and damage will occur. Let's take a look at total joint dimensions. In addition to thermal, moisture, elastic, and creep deformations, there are several other factors that should be considered in determining the joint dimensions. One such important consideration is material tolerances, to recognize that building components vary from their specified dimensions. For example, it is not uncommon to see a brick or concrete masonry units that are undersized or oversized. Noticeable differences in dimensions from those stated on the drawings can occur in prefabricated concrete curtain wall panels. In addition to material or component tolerances, construction tolerances should be taken into account. For example, an expansion joint in a masonry wall may be shown as a vertical joint on the drawings, but the constructed joint is unlikely to be absolutely vertical. Construction tolerances are a function of quality control during construction. Most joints in building envelope components are filled with elastomeric sealants. The sealants have a finite ability to cyclically stretch and compress, which is given as a plus-minus movement ability of the sealant. The plus value denotes the maximum stretch the sealant can withstand, and the minus value denotes the maximum compression it can sustain. In fact, sealants are generally classified based on their movement ability. Thus, a sealant with a movement ability of plus or minus 25% is called a class 25 sealant. Such a sealant is able to stretch and compress by 25% of its installed dimension. Similarly, a sealant with a movement ability of plus or minus 50% is called a class 50 sealant. Thus, the width of the joint at the time the sealant was applied is at 1 inch. A class 50 sealant will safely stretch to 1.5 inches or compress to 1/2 inch. So our previous example of the 25-foot long brick veneer wall, we're going to take into consideration both thermal and moisture movement. And so our thermal movement on that wall segment was 0.108 and our moisture movement was 0.09. So the equation we use is we basically would just add those together. We end up with 0.198, and we would multiply that number by 2. So there should be plenty of extra movement that's allowed in that joint. So our total number here is 0.396, and with typical construction tolerances, that 0.396 would turn into 1/2 inch wide joint. Let's take a look at principles of joint detailing. In detailing a movement joint in a component, it is important to distinguish between an expansion joint and a control joint. Because the joint width in an expansion joint will become smaller over time, the filler in an expansion joint must be elastomeric to allow unrestrained movement of the components. So this is the detail of an expansion joint. You can see that they have what they call a backer rod here. This is a compressible backer rod, and the elastomeric sealant is the yellow portion here. So as the brick expands, the material in the joint compresses, and the sealant allows for the wall assembly to stay dry. This is a detail of a control joint in a concrete masonry wall. So the previous example, we looked at clay brick, and clay brick, as it comes from the kiln, it's completely dry, so clay brick is going to expand. And in this case, with concrete masonry units, it's a wet material, so over time the moisture or the material is going to dry out. So in this case, it's going to shrink, and the joint is going to pull apart. So we must use some kind of a bond breaker. So if I have a control joint at the ends of two blocks, I've got to allow for movement in here. So a bond breaker is used inside on one side of this voided cavity area. So that allows for the joint material, the backer rod, and the sealant to stretch. The primary purpose of sealing a joint is to prevent water penetration. However, control of air leakage, dust penetration, and noise transmission are additional benefits of sealing a joint. An unsealed joint may also get filled with incompressible materials over time, resulting in joint failure. Although joint sealant is the most important component of a sealed joint, these other components must also be carefully selected: substrate, primer, sealant backup, and bond breaker. For a sealed joint to function effectively, it is important that the sealant be fully adhered to the surfaces of components meeting at the joint, called the substrate. The purpose of primer is to improve the adhesion of sealant to the substrate. Some sealants require primers on all types of surfaces, whereas others require primers on only few types of surfaces. The sealant must have backup. So there's a backer rod. The sealant backup is a compressible and resilient material, such as a plastic foam. It is usually circular in cross-section. So in this case, with these two examples, it's important to note the difference between the untooled and the tooled joint. So if you look at the untooled joint, you'll notice that the substrate is not fully covered. So the bond is not going to be as good as the tool joint. And if we look closely at the tool joint, you'll notice that more, if not all, of the substrate is covered, creating greater adhesion and greater stretch in the material itself. Elastomeric sealants are synthetic materials and are the ones most commonly used in contemporary construction. There are 5 commonly used synthetic sealants, and they are polyisobutylene, acrylics, polyurethane, polysulfide, and silicone. Polyisobutylene and acrylic sealants have very low movement ability and are used as caulking materials in joints that do not move or move very little, such as static joints between aluminum window frames. Polyisobutylene has excellent resistance to water vapor transmission. Therefore, it is commonly used as a primary seal in an insulating glass unit. The secondary seal in an insulated glass unit is provided by the silicone sealant because of its durability and good adhesion. This is the end of Chapter 9, Part 2. Go ahead and complete the quiz for Chapter 9, Part 2 now.